Today we're going to talk about dark matter. One of the most interesting things about the universe that we found so far is that a large fraction of the matter in the universe is stuff that doesn't interact with light or electricity and magnetism. And this stuff exists, it's detectable via gravity, but we don't see it interacting with light. We don't see light shining from it, we don't see light reflecting from it, and we don't see light absorbed by it. So today I wanted to talk about why we believe this stuff is there, the evidence for dark matter, and some of the indications of the amount of material that's out there and how we might go about finding more information about it and its characteristics. So this picture that we're looking at right here is a cluster of galaxies, and we're seeing pretty much everything in this field of view is a galaxy of some kind, so these are galaxies. And one of the things that you'll notice around this image is these little arcs of light. And if you look at those things really closely, you'll see that they're smeared out images of galaxies, and that smearing out of the image is caused by the light being bent by the gravity in front of it. So we have got a foreground cluster right here. It's a big massive object. We've got background galaxies where the light is coming around the massive object, and it's getting distorted as if it was a lens in front of that. This gravitational lens, as it's called, is merely, according to Einstein's relativity, light being bent by gravity, but it allows us to weigh the amount of mass that happens to be in this foreground cluster. And just to give you the punchline of today's topic is that the mass that we measure via this gravitational lensing is far greater than the mass that we see emitting light. So there's something out there in the universe which is physically real, interacts via gravity, but does not interact via electricity and magnetism. So let's see if we can figure out what this stuff is and what its properties might be. So the first thing I want to do is talk about how we weigh things with gravity. And this is something that happened just recently in today's newspaper. We've discovered a couple of planets out, and one new planet out in the outskirts of the solar system, and that planet is a small dwarf planet much like Pluto, but its orbit is being sculpted by other planets in the solar system. And so there's a suggestion that there could be as much as a 10 Earth mass planet out at 250 astronomical units, which is sculpting the orbits of these dwarf planets. Now, if such a thing exists, we haven't yet to find it, and in fact, if it's that far away and that small, we don't have the technology to discover it. And so we have to think about other ways we might detect it. And the other ways we detect it is by looking at the orbits of material in the solar system. So we can look at the orbits of other bodies to detect planets in our own solar system using gravity. Now this is analogous to what you did when we dropped marbles from the balcony to measure the mass of the Earth, where we're using gravity to measure the existence of the planet Earth. And you can do that experiment even if you can't see the Earth itself. So let's talk a little bit about orbits and why they move, and see if we can connect that back to the masses that cause the orbits to move. So what we're looking at here, this is a map of the inner solar system. We've got the Sun right here, we've got Mercury, Venus, Earth, and Mars, and all these things are going around the Sun according to Kepler's laws. So if I can measure the orbital period of one of these objects, I can determine how much mass is interior to its orbit. And this is just a little simulation to show how that works. If I click on a certain orbit, I measure its orbital speed, and then I click out the next orbit, its orbital speed is lower because of Kepler's laws. If I click on the orbital speed, it's a little bit lower, Kepler's laws. If I click on it again going out, again we see Kepler's p squared equals a cubed relationship, and we watch the orbital velocity drop as a function of distance. So I can use that information to discover the Sun. Now I don't have to discover the Sun this way because I can see it, it emits light, but even if it was a black hole that emitted no light, I could detect it using these orbits. And this is a little simulation just showing how we could do that. We could say, well, let's look at the orbit of Mercury, and if I imagine using the orbital velocity of the orbit of Mercury, I can figure out how massive the Sun is, or at least how much mass is interior to that orbit, by measuring the orbital speed of Mercury. And if I do that, I get that there's one solar mass of material. Now I can do the same experiment and go out to Venus's orbit. If I do that again, I get one solar mass of material, because Mercury is not that large. Even though Mercury is interior to Venus's orbit compared to the Sun, it's minuscule. I can go out to Earth's orbit and I should still get a mass of 1. I go out to Mercury or Mars's orbit, I get a mass of 1. Right? You see where this is going, that the Kepler's law is telling us about the mass interior to the orbits. And that's an equation that we've seen before. This is a combination of the orbital velocities and Newton's version of Kepler's law. We can see that there's a relationship between velocity, distance, and mass. And for the case of the solar system, almost all, 99.999% of the mass of the solar system is in the sun. So we get the same answer regardless of the orbit that we look at. So that's how we can measure the mass of things using the sun. Now, the question becomes, how do we look at things like galaxies to see what their masses are? Could we use something similar by charting the orbits of stars? And the answer is we can do that. We can look at the orbits of stars in a galaxy to determine the same thing. In the spiral galaxy, the stars are orbiting it, and it's in a way analogous to a solar system. We have some central mass. It's brighter there. There must be some concentration of mass there. The mass drops off as a function of distance. All these stars are orbiting around that we can see. So we should be able to take a galaxy and do the same experiment. We should be able to go and pick a star using Doppler shifts to figure out its velocity, so pick a nice edge-on galaxy and look at the velocities of the stars in the galaxy to measure the mass interior to those stars. The only trick is that inside here there's so much stuff that it doesn't operate like a Keplerian orbit. There's an analogy to what the interior of a galaxy looks like, and that is, imagine you're on a merry-go-round, right? And your orbit, rather than being governed by Kepler's laws, is governed by sort of a solid disk rotation. There's so much material in there that that you're not able to orbit with Kepler's laws, and instead you orbit more like a solid disk. Well, if you've ever been on a merry-go-round, you'll know that since every single person on the merry-go-round has to traverse the same angular distance in the same amount of time, that if you're at the edge of the merry-go-round, your velocity in terms of meters per second is faster than than if you're interior or closer to the center of the merry-go-round. So this person can go slower because they have a less physical distance to go. This person has to go faster because they have further distance to go, even though they're going around the same angular 360 degrees each time. So what does the rotation curve look like for a galaxy if it operates like a merry-go-round in this center bit, right? Well, we can look at orbital speed versus distance on a merry-go-round. And again, if I click on the center, that's pretty much 0, 0, right? You can stand on the center and you not go around very, very fast. But as I go out, if I just keep picking places that are further out, I get this linear relationship. You can see that the line it's just a linear relationship between distance from the center and orbital speed. So what I would expect from galaxy rotation is a linear relationship close in to the center of the galaxy. Now, if I were to look at the relationship as I got further out from the galaxy, if I go back to my galaxy picture here, you can see that the density of material appears to drop off. There's less stuff we can see. So what would I expect? I would expect that it would operate more like a solar system. So on the exterior of that central bright region, I would expect something that looked more like this, right? That looked like our Keplerian velocity. So if I imagine drawing in what the interior of the disk should look like, the interior of the disk should be kind of this straight line. And as you go out on the disk, it should drop off by Kepler's law. So this is the shape of the velocity profile of a galaxy that I expect, assuming that all of the mass that I can see is in starlight. Stuff that I can detect with my electromagnetic detectors, such as my eyes or a radio telescope or something like that. So we can do this experiment, right? We do this experiment and we look at a spiral galaxy and we look at the orbital speed, right? So the orbital speed, I'll just click on various areas here in the center. As I go out from the center, you see that it's a line, right? I've got a line pretty much going straight up. So as we're seeing this non-Keplerian rotation, this solid disk rotation near the center. But as I go out further, I see it start to roll over, which is what I expect. It's rolling over. And right at this point, we expect that if there is just visible matter, this should kind of go like that. Okay, so let's see what happens when we do this. So that's what we expect to see. So we start going further out, further out, further out. And at first we follow that curve, and that makes sense. And then we find a few stars out here. and all of a sudden we see that there's a departure between the solid disk Keplerian model that we had and what's actually going on. And if I find stars even further out, we'll see that the galaxy rotation is flat. So what we observe with galaxies is this green line. We see the solid disk rotation, we see the curve, and then we see it just go out straight. So what does that mean? What that means is that there must be some material interacting gravitationally with the stars that we can't see. Now this could be, in principle, things like a black hole. Right? Black holes are things that we can't see. They don't emit light, so we can't see them. So that's one possibility. There could be brown dwarfs or small failed stars. Those would be very difficult to see, at least at galactic distances. It could be rogue planets, planets that are thrown off from various star formation events. So you could imagine a situation where there might be stuff that if we were close enough we could see it and it would emit light, but we don't see it because it doesn't emit very much light. Okay, so that would be like your regular garden variety astronomy stuff that we know about already. However, you can do experiments in our galaxy and find out that that stuff is not really enough to make up this difference. You know, it might raise it up by that much, but it's not enough to raise it up by this. In fact, in order to get this raised velocity profile, you need something like 90% of the mass of the material has to not be in stars, and it has to be in these other dim objects. And think about that for a minute. In our solar system, 99.999% of the matter is in the sun. So even if the sun threw all of the planets out, that would not be enough to account for an additional 90% of the galaxy, right? So it's got to be something more exotic, something we've never seen before, and something that may not even interact with light at all, or at least very, very, very weakly. Okay, so this is the first piece of evidence that we have dark matter at all. What does this tell us, though, about the interior of the galaxies? Well, I can begin to do the same thing. I could use the same equation that I had before to measure the mass interior, because I just need a velocity, I need a distance, and I need the gravitational constant. So let's go ahead and do that. So I can pick a star and get the interior mass. Pick a star again, get the interior mass a little bit further out. I keep doing that, and we see that as we go out to the visible material, the interior mass goes up, and that's what we expect because we see more stuff in the center, and so as we go further out. But you'll notice there are no stars out here, and if I continue to weigh the galaxy out to this distance, it continues to go up, way up here. And in fact, it keeps going up until we run out of stars to use as tracers. So what that tells you is that there is material all throughout this region which is not emitting light, it's not reflecting light, it's not absorbing light. And it represents 90% of the mass of the galaxy. A huge amount. Right? That's a factor of 10 increase, right? Or a factor of 2 increase right there. But it also is part of the contribution down here. So this is the stuff we call dark matter. And again, we call it dark matter because we can't see it. But this is a trick that astronomers use, most scientists use when we discover something. We don't know what it is, we don't know what its properties are, so we name it and then see if we can figure out how it interacts with other things in the universe. And while we're doing that, we pick away at what the properties of this material might be until we can figure out what it is. Right now we're at the phase with dark matter where we know it exists, we know how much of it there is, we know how it interacts via gravity, and that's about it. And that's what we're going to be talking about today. But before we get on to what dark matter could possibly be, let's look at some other pieces of evidence for dark matter, because this is a pretty outlandish claim I'm making. I'm saying that 90% of the universe, you can't see it, but it's there. Okay? And if anybody came up to me on the street and told me that, I would want some pretty substantial evidence that they were right. Okay. So in our solar system, if our galaxy, we do this, we can measure the orbit of the sun. This is something that we can do from our own solar velocity, and we find out that the sun's mass, the sun's orbit encapsulates a mass of the galaxy of about 10 to the 11 solar masses. When we look further out at stars that are further away from the center, we see that there's about 10 to the 12 solar masses, and we cannot account for that material with the stars themselves. If you think about, there's about 10 to the 11 stars in our galaxy, and on average they're about a solar mass, and so just doing that rough calculation tells you that our galaxy is 10 times more massive than it should be based on the stars alone. Now, how do we measure these velocities we've been talking about? It's very hard to find individual stars in distant galaxies, so instead what we do is we find a galaxy that's relatively, edge on to us, so we can measure the velocity via Doppler shift. So we look at the stuff moving towards us is going to be blue shifted, the stuff moving away from us is red shifted, and how much it's blue shifted and red shifted tells us the velocity in meters per second. Okay, so we can tell what the velocity is, and we get a information about that velocity all the way out, so we can draw these velocity curves. Now here's some examples of velocity curves that have been measured for different galaxies, and it's interesting to see that there must be some distribution of dark matter, because if we look at, say, in UGC 2885, on all of these we see this steep linear rise, and then this one you actually see a Keplerian drop-off before it goes back up like that. So what does that mean? That means that we've got a solid disk, kind of interior, if we imagine our model here. We have material that just acts like a planetary system out here, and then there's got to be some more material out here which is causing the flat rotation curve. So there's clearly clumpiness to the dark matter. So it has some structure, it has some dynamical properties. You can see some of them, like this one, oscillate, right? It oscillates around kind of a constant velocity. So this one does it too. It tells you that there's, like, Kepler takes over, then the dark matter takes over, then Kepler takes over, dark matter, right? So there's some structure to that. And then there are even some that we get a little Keplerian drop-off, and then which means the density of the dark matter has to be going up as you go out. So that means that this stuff we can't see. It's not just some haze that we can't see. It's got clumpiness, it's got structure, and its structure, frankly, is probably just as complicated as the structure we see in spiral galaxies from the light and from the stars and the gas and the dust. So dark matter is an interesting bit of material here. Now, what other piece of evidence do we have? This is our model for our dark matter, where we have kind of a luminous matter in the center. We have this dark matter halo, and we don't see what the dark matter is, but this is the structure of the material. Now, dark matter is important because it's this material here that is dictating the shape of the material in here, and the shape of the material in here determines how many stars are formed, and how many stars are formed determine U. So in a very real sense, we are connected to the dark matter distribution of the galaxy, because the dark matter distribution of the galaxy is driving star formation, which drives planet formation, which drives people formation. So it's important to kind of keep that in mind, that this is all connected all the way through. The other way we can do this is look at clusters of galaxies. So same thing with regular galaxies. If you look at the velocities of clusters of galaxies, right, look at how these things are moving around each other. Their motion is going to tell you about the mass interior, right? And we can do that and find out that we get about 50 times the amount of mass that we expect from stars in clusters. So what that tells us is that dark matter dominates more and more and more on larger and larger scales. Okay, so on the solar system scale, there's no dark matter in our solar system. It's all in the sun. Visible matter. We get out to the galaxy, about 10 times the amount of the galaxy is dark matter. We get out to clusters of galaxies, and 50 times the visible matter is dark matter, right? So it becomes a very strong component of the universe. One other piece of evidence, just in case you didn't have enough at this point, we can look at the temperature of gas in these clusters. So this is looking at X-ray emission, and X-rays are associated with high temperature materials. The reason that we look at the high temperature is because you need a lot of gravity to keep high temperature gas around, because it's so kinetically energetic that it's just going to dissipate. So if you see a big clump of highly energetic material emitting X-rays, you know there has to be a ton of gravity there holding it together. And so when we do that, we see that there's about 85% of the material in here has to be dark matter, about 13% hot gas, and 2% stars. So the visible matter in here is very, very, very small. All right, the last piece of evidence I'm going to give you is something called gravitational lensing, which I alluded to earlier. I've got a little video here to show you about that. So this gravitational lensing, you imagine light from a distant galaxy coming at the Earth. If there's nothing in the way, it goes straight at us because it travels on a straight line. But if there's a cluster of galaxies in the way, those clusters of galaxies are going to bend the light and cause this pattern, this kind of lensed pattern of galaxies. You can see these things right here, right? These arcs of galaxies from the background object. That allows us to measure, since we know general relativity, to measure the mass in between us and that galaxy. And so when we see a picture like this, where we see a distant galaxy that's been lensed, and you can see that this galaxy is the same galaxy because you see the same structure. It's a little distorted, but you see the same structure in all of the little images formed by the lens. Right here it is again. Just like if you were looking at it through kind of a lens that wasn't in focus, if you were looking at something in the background through the lens. So we know this is the same distant background galaxy right here. We see these images of the galaxy, and how much this deviates as an angle from this center line tells us how much mass there is in the middle. If it doesn't bend very much, there's not very much mass. If it bends a lot, then there's a ton of mass. So we can use this again to weigh the clusters, and you guessed it, there's more mass than we can see. Okay, so that's the evidence for dark matter. Dark matter is the material that that interacts with gravity that we can't see. There is another piece of the puzzle here in early cosmology, and that's something called dark energy. This was discovered with looking at the expansion rate of the galaxy. We talked about the Hubble expansion. You remember our Hubble expansion had a constant expansion, at least in the nearby universe, with distance of the velocities of galaxies. Right? So we measure these galaxies and they had velocities like this. Well, it turns out if you do very careful observations of distant galaxies, they're actually going a little, accelerating a little bit, right? So there's a force of the expansion of the universe that's changing and pushing the universe apart faster and faster and faster. This is due to the energy density of the within the universe, what we call dark energy. Now again, this is something that we don't really know what it is, but it's required in order to make the observations that we see match with our theory of the origin of the universe. So there are these two properties. Dark energy, you can think of dark energy as the thing that's pushing the universe apart, and you can think of dark matter as the stuff that's holding it together. And there's a competition between these things, which right now dark energy is winning. Right? Dark energy is pushing apart faster than dark matter can haul it together. So again, we can detect the dark matter from its gravitational influence, and we can detect the dark energy from its repulsive force against the expansion of the universe, causing it to accelerate. This, just as a point of note, the folks who figured this out, I happen to be an office mate with one of the Nobel Prize winners for this, and it's pretty cool to think of somebody in my generation getting Nobel Prizes for figuring out this really cool stuff. Okay, so now we can take kind of an inventory of the universe now that we have all these data and figure out how much of the universe is part of these different components. Now again, we remember with Einstein, in addition to general relativity, we have the most famous equation in the world, E equals mc squared. The universe has a sum total of energy, right? Some of it is distributed in mass, some of it is distributed in energy, but since they're interchangeable currencies, if you will, we can talk about the total energy density of the universe or the total mass density of the universe. Either way, it's just a way of accounting for what the universe is made out of. And if we do that, then normal matter, so this is U, stuff like U, this is hydrogen, mostly helium, and then stuff like carbon, nitrogen, oxygen, sulfur, phosphorus, right? Stuff like that. That is 4.4% of the universe. And the stuff that's inside of stars is 0.6, and the gas and dust that make up the galaxy are 3.8. So this is where you are, right in here. And that's all of the stuff that we've ever interacted with physically. Every time you pick up an object, every time you touch anything, every time you look at anything, we're looking at normal matter that's governed by normal chemistry. 25% of the remainder of the universe is dark matter, which is stuff we can't see but is influenced by gravity, so we can detect it via gravity. And then 71% of the universe is this dark energy, which is driving the universal expansion, which means that roughly all, so something like 95%, 96% of the universe is stuff that we can only see indirectly. It's nothing in our room is this stuff. So this is pretty staggering to contemplate, that most of the universe, in fact, a large fraction of it, is stuff we've never even seen before. We've only indirectly detected. Now, you might ask yourself, does dark matter really exist? And I hope I've given you enough evidence to suggest that it does. But we have to think a little bit about what are the options and what can we do to get more evidence to test these ideas of dark matter and dark energy. So these are our options if we think about this scientifically. One is that we really are seeing dark matter, that our theories of gravity and general relativity are correct, and we are observing the effects of gravitational attraction on dark matter. Now there's a second option. That option is that something is wrong with our understanding of gravity, and that's causing us to mistakenly infer the existence of dark matter when what's really going on is we have a problem with our understanding of gravity itself. Okay, so these are our two options. And the reason that we go with option one is because every single experiment we've ever done has tested gravity. Right? Every single one of them. However, there is one thing I want to point out, that we are now just, my dog's barking. We are now just beginning to test gravity on the largest time scales, largest distance scales. So this is an avenue, or I should say an area, that we haven't tested gravity on before. So it's still entirely possible that there's something about gravitational interactions on really big distance scales that are different from relativity, just like relativity is different from Newton at very, very fast speeds. Right? So we're testing a new realm. So we can't rule out number two altogether, but because gravity is so well tested, we really do lean towards one. And there's a second option too. The second option is that we can, or the second reason why we lean towards one, is because we can build telescopes and detectors here on Earth to measure dark matter particles. We come up with theories for what they could be, predict what experiments could be done, and then we look for them that way. Whereas if something's wrong with gravity, we have to have theorists working on that, and we do. Theorists work on what's wrong with general relativity, and maybe one of them will come up with an idea, but you can't really beat on it the same way that you can work really hard on observations, because you really just have to wait until the idea percolates up from somebody before we know what's going on. Whereas with experimentation, we can build detectors that will just find what's out there, and that's why we've been going in that direction. Okay, so what's our options? Let's take for the sake of argument that dark matter really does exist, because we've seen the evidence for this. Since we have so many lines of evidence, it's hard to imagine us getting this completely wrong. So let's look at what dark matter could possibly be. First of all, we have to ask, how dark is it? Right? Is it something that is just not as bright as a star? If that's the case, then maybe it's something we could detect with electricity and magnetism. So that gives us these two basic options. One are these things called machos, for massive compact halo objects. These would be things like white dwarfs, black holes, failed stars, big planets that got tossed out, that are real, just regular matter that we don't see because it's so far away and so faint. Okay, so these are this is a possibility. However, there has been an experiment to look for this in our galaxy, and they didn't find it. So there was some, a few percent, but they really didn't find any. So this one's kind of not looking too good right now, because in our galaxy anyway, where they are close enough to see, we don't see them. Other possibilities are we have something called extraordinary dark matter, which would be weakly interacting massive particles. So in other words, these are a particular particle or a host of particles that weakly interact with electricity and magnetism, so we don't see them, but they permeate the entire universe. One particle like this is something called the neutrino. This is something that's created in solar fusion events that streams out of the sun, hardly interacting with the sun at all. It's very, very weakly interacting, but it does have mass. So if you have neutrino-like objects, and we know of some things like that, if there are enough of those in the universe, they could account for all the dark matter. So the machos are things that we build telescopes to find, and we're still doing this because maybe there's something we don't know about out there. And extraordinary dark matter are things we build particle accelerators to find, to do particle acceleration experiments and particle collision experiments. And the nice thing about both of these things is that both the telescopes and the particle accelerators tell us a ton about the universe's physics, even independent of dark matter. So we get a lot of scientific results from both of these types of events while we're searching for these things that happen to exist. This is the best bet for now. So if you want a job as a physicist in cosmology and you want to look at dark matter, you probably should go work in a particle accelerator. Okay. So that's our introduction to dark matter. Next time we're going to be talking about the distribution of galaxies and how all of this stuff affects the formation of our own galaxy. But for now, you can just go forward and imagine a universe where 96% of it is stuff you can't see.